Hello, and welcome to Chapter 2, Section 2. So today I want to talk about density curves. This is something new. So basically, a density curve, if you look at a graph, we've been talking about histograms a lot. So generally, if we look at a histogram, oh my goodness, and kind of look at like an overall outline of the graph, so like what you see in red right here, that's a density curve. So basically, just a general outline. So two rules about density curves is that they always have to be on or above the x-axis. And then the second rule is that underneath the curve, it has to have an area of 1. Or if you like to think about it as like 100% of the data points are under the curve, which makes sense. So when we deal with density curves, what we're mainly looking for is the area underneath it. So we know the full area has to be 100% or 1. Then we can start looking at like different portions of the area. So let's do an example together. So here's my density curve. We're talking about people's GPAs, and then on my y-axis I have relative frequency. So since GPAs only go up to 4.0 for unweighted, then we're saying in this graph that we have basically like an even amount of people between 2.0s to 4.0s. So this is a uniform distribution because it is the same height all the way through. And then because our density curve, it looks like everyone has GPAs between 2.0 to 4.0. Nobody has any GPAs below that. Then our relative frequency here, the highest it'll go is 50%, because in order for our area underneath the curve to be an area of 1, it's a rectangle, so it has a width of 2, and so the only height that it could be is half, or 0.5, in order for it to make an area of 1 in total. So our first example, we're going to find the percentage of people with a GPA between 2.5 to 3.5. So if I were to draw that out, it would kind of look like this. It would be these people here from 2.5 to 3.5. So we're basically looking for that area whenever we're trying to find like a percentage of people at this point under a density curve. So that shape right there that I've shaded in, it's a rectangle. I know it's ugly, but it is a rectangle. So to find areas of a rectangle, it's just length times width. So between 2.5 to 3.5, that's a width of 1 times the height of 0.5. So when I multiply that out, I get basically 50% of people have a GPA between 2.5 to 3.5. So next I want to find the proportion of people with a GPA between 2.0 to 3.8. So when you see the word proportion, it just means percent. Proportion, percent, fraction, decimal, all the same thing. So this time, instead of looking at our density curve from 2.5 to 3.5, we're looking from 2, which is right here, to 3.8, which is like here. So we should be getting a much bigger percent because we're shading a lot more area. So again, it's going to be a rectangle. So length times width is going to be a length of, or a height, whichever you want to call it, of 0.5 and a width of, what is that, 1.8? Because from 3.8 to 2, there is a width of 1.8. And when we multiply that together, I get 0.9, so 90%. So if you've been looking at my work right now, I've been answering in either decimals or percents. Both work because decimals, percents, they are the same thing. So however you want to answer it, that's why we also said when we talked about the area of 1 versus 100%, those are the same thing. Okay, so for my last example in this scenario, I want to find the proportion of people with a GPA of exactly 2.5. So looking at my picture here, I just want the people who have a GPA of 2.5. So if I were to draw that out, it'd be like right here, just that line. I'll make it solid instead of dotted. So just that line of people who have an exact GPA of 2.5. I don't know about you, but can you find an area of a line? Because that's really all we have. We don't have any like shaded portion. So in that case, find the proportion of people with a GPA of exactly 2.5. This is a 0% because it has no area. It's just a line. This is a 2D shape. So there's no area to it, so that's why it's 0%. So anytime you're trying to find like exactly a certain number, it's always going to be 0. But if you can actually find the area or something, then that's how you're going to be able to find the percent. Alright, this time I want to do a different example with a different density curve. So this time, instead of a rectangle, we have a triangle. Ooh. So this time, I'm also going to write my problem out a little bit differently, just so you can see all the different ways that you can be asked. So here, in this example, I've written it out as like capital P, parentheses, 0 less than x less than 2, parentheses. So this is another way of asking, like, what is the proportion or the probability of? So maybe you've seen this before, like f of x, like where we have f parentheses x. This is just a function where it's like p of x. So just a different name. We use p to stand for proportion or probability. So just get used to like seeing that, because we're going to use that a whole bunch this year. But in this case, what x is actually standing for is like our GPAs. We're saying what's the proportion of GPAs between 0 and 2, because it has to be less than 2 but greater than 0. So in that case, we are looking at this area right here. There's my shading, blah. Okay, so triangle shape, which means we need the area of a triangle. Hopefully you remember area of a triangle is 1/2 base times height. Okay, so using that, we have the base of our red triangle is going to be 2, because we're going from 0 to 2. And the height of this triangle then would be the 0.5, because that's how far the relative frequency goes. So when we multiply that out, you should get 0.5, or 50%, which makes sense. That was half the triangle. So even if you could tell right away from the triangle being 50% shaded, done. You don't have to use the area formulas every time. Okay, let's do another one. This time we're looking for x being between 0 and 1. So if you had a GPA between 0 and 1. So same thing, let's use our area formulas here. Between 0 and 1, that's a base of 1. And a height at that point, oh, I didn't even draw it out for you. So one's like right here. There's my shading. Okay. So, excuse me. We're trying to find the height of that triangle right there. A little bit awkward because I don't actually know. It wasn't labeled for me, but we could figure it out. Because, you know, math. So if you look at this line segment right here, between 2 to 0.5, it has a slope of rise of 1/2, a run of 2. So rise over run, the slope would be 1/4. So then at 1, this should be also 1/4, or 0.25, in case that wasn't obvious to people. Okay, so then our height's going to be 0.25. Multiplying that out, I think we get 0.125, or 12.5% of people have a GPA between 0 and 1. Cool. We're hoping that's a low number, because you don't really want a GPA of that. Alright. This time, let's look at a GPA between 1 and 4. So this time, notice I did less than or equal signs, because if I were to draw this out, let me erase this last one. So if I were to draw this out, whether I do dotted lines or solid lines at 1 up until 4, the area is still the same. That's what I wanted to point out. So whether you use less than signs or less than or equal signs, they are the same area, because like we said earlier, the area of a line is 0, so it really doesn't affect the overall area at all when we're looking at areas of density curves. So between 1 and 4, we just need to figure out like the area of the shape here, because we have like kind of a triangle. but like added stuff to it. So if you want to split this up, like I tend to like to split this up into like, I don't know, here's a triangle, so I could find that area first, which was 50%, because that's half the triangle, and then I could figure out this area here. But also we said this area here on the left, we just said this was 12.5%. So if we're basically shading like the entire thing except for that 12.5%, really, I know the area of the whole entire density curve is 1. So I can just subtract out that 12.5% to get the rest of it, which will give us 0.75, which is 87.5%. So that's another way, that's why knowing that the area, overall area is 1 is useful, because we can always subtract rather than like finding areas of parts. Alright, for this last example of this graph, we're going to look for the proportion of people with a GPA between 1 and 3. So, drawing out my picture, I've got this red portion shaded, and then I kept that 12.5 on the outside from the last example, but looking at our graph, we know that this triangle is symmetric, so looking for this red area, rather than, this is a weird shape again, I can just subtract out the two sides. So I can subtract out the 0.125 from the left side and the 0.125 from the right side, and then that'll give me the center area. So when I do that, I end up with 0.75, or 75% of people have a GPA between 1 and 3. Done. Alright, next I want to talk about a very specific density curve, and this is one that we will use for the rest of the year, like in every single chapter that we do from now on. So this is called the normal curve. You might have seen this curve before. It's basically the bell-shaped curve. So in this bell-shaped curve, we have a curve that's symmetric on both sides. So if you imagine like a histogram being a bunch of bars within it, and then we're drawing a density curve of that like overall shape around it. The mean would be right in the middle. Because it's symmetric on both sides, the mean, the median should both be in the middle. So we're using this symbol mu that we talked about in last section when we looked at the z-scores. So mu stands for our population mean, and this is different than our sample mean, the x bar. And then if you know calculus or have heard of, or have taken calculus before, this point out here, this is called the inflection point, and it's not that important. You don't actually need to know what this is, but if you're in calculus, fun fact, the inflection point is where it goes from concave down to concave up. So right when it switches like that, that's where this distance is important. So this distance here, for the sigma symbol that we used last time, this stands for our standard deviation of a population. So that population standard deviation, we're saying like from the inflection point to the mean, that distance is how far a standard deviation is. And this is a normal curve is really important for us to use z-scores for, and that's why we learned about it last time first, because we're going to be finding those percentages under this curve using those z-scores. But before we get there, I want to talk about the normal curve a little bit more. So this curve here is specifically called the normal curve, not like it's normal or not. Like we capitalize the N for normal to show that this is the normal curve. And then within the normal curve, or a normal distribution, if you have a distribution of data that's normally distributed, then there's certain percentages that we want to look at. So I've redrawn my normal curve. This time I've drawn lines where it covers all the data points that are one standard deviation away from the mean. So if I added a standard deviation to the mean and got to this distance here, and I subtracted one standard deviation away from the mean and got this distance here, then everything in between, it's a very specific percentage that this covers. So everything in between one standard deviation includes about 68% of the data. And if I kept going one more standard deviation away from the mean, so now we're looking at the mean plus 2 times the standard deviation, and the mean minus 2 times the standard deviation. So we're basically going twice that distance over. Everything in between those two numbers includes 95% of the data. Okay, and we can go one more standard deviation over, all the way out here. Let me extend my normal curve a little bit, because technically the normal curve does go on forever in both directions. It's technically like follows an asymptote, if you remember that word. So it's the line that a graph never touches but approaches. So it does technically go on forever in both directions. We just don't draw it out because we don't have that kind of paper. But 3 standard deviations out from the mean would give us the mean plus 3 times the standard deviation, mean minus 3 times the standard deviation. And between those two values, oh gosh, 99.7% of the data falls between those two values, which means everything outside of that, that's where we like stop counting anymore. Everything outside of that would be the rest, because this is a density curve, so the total area has to be 100%. So really that means on the outside of 3 standard deviations away, there's 0.3% of the total data. So those are like the people who are, or the data points that are like super outliers, because they're so far from the mean. So this rule right here is called the 68-95-99.7 rule. It's also called the empirical rule, and I refer to that more often just because it's easier to say, but you'll see them referred to in both ways. So when we talk about anything that's normally distributed, it follows the normal curve, and so all your data points will fall within these percentages, proportions, when we're looking for the proportions of whatever our data is. Let's do some examples. Okay, so for this example, I've got the mean batting averages for 432 Major League Baseball players was 0.261 with a standard deviation of 0.034. Suppose that the distribution is exactly normal. So they're telling us it's going to be a normal curve because they said the distribution is exactly normal. So, clue right off the bat, draw a normal curve. There it is. And then they're asking what percentage of batting averages are greater than 0.329. So what we want to do first is set up our normal curve so that we know where all the numbers are. So I'm going to draw this out. It doesn't need to be like super accurate at this point. We know what it's supposed to look like, and that's good enough. So I have the mean right in the middle, and then we're going to look at the 3 standard deviations on both sides of the mean. So draw 3 lines next to it. They told us the mean was 0.261 and a standard deviation of 0.034, which means to find the rest of my numbers, I want to keep adding and subtracting 0.034 from 0.261. So I'm going to do that real quick, because 0.261 plus 0.034 will give me 5, 9, 2, and then you keep going. Okay, so I've added and subtracted by the standard deviation of 0.034 all the way through on both sides. So at this point, they're asking us for the percentage of batting averages that are greater than 0.329. So I can see 0.329 right here, and they're asking for this area then. So every single time I'm going to draw my picture in shade just so I can see visually like where I'm trying to find the area. So this is when I want to use the empirical rule, because I see that the 0.329 is 2 standard deviations away from the mean, because I had to go 2 lines over, which means that 2 standard deviations away, I know like right in the middle of the 2 standard deviations away is supposed to be 95%, according to the empirical rule. But we want the outside area of that. So if I know 95% is in the middle here, that means if the total area is 100%, then 5% has to be on the outside of both sides. So on the right side and the left side should total 5%. So if I just want the right side, then I can split that in 2 to get 2.5% of everything greater than 0.329. So that was my reasoning, my thinking for it. Let's do another example so you can see how to think about these. Okay, so this time I'm looking for the percent of batting averages that are between 0.193 and 0.295. So looking at my picture, I've redrawn it just so it's easier for me to see. But 0.193 is here, and 295 is here. So I want this area in the middle. Okay, well, let's see. So I know the 0.295 is 1 standard deviation away from the mean. So we know, according to the empirical rule, 1 standard deviation away is 68%. So I know most of it now. I just need like this leftover area right here on the left. So we can try to figure that out by looking at, let's see, I know 2 standard deviations away, because the 0.193 is 2 standard deviations away. It's supposed to be 95%, but I already know that the middle portion is supposed to be 68. So if I subtract the 95% from the 68, that'll give me the areas that are here. This part and this part. If I took the 95, subtracted the 68. I believe that's 23. Nope, just kidding. 27. My math skills, so good. So 27% is what's left over. So everything in blue right now would be worth 27% of the data. But we are only looking for this left side blue. So if I split that 27% in half, then that should just give me one side. So I know this is actually going to be 13.5% then, because that's half of 27. And then plus this middle 68%, that should give me the total between the 0.193 all the way to the 0.295. So adding that together, I get, oh gosh, math, so difficult. 81.5%. Yeah, adding skills. Okay, so this is the general type of way of thinking that you want to use when we are trying to figure out areas of normal curves. So using those 68, 95, 99.7 percentages, use those to kind of figure out the rest of the sections. And this comes with practice, so we will be doing a bunch of practice in class. But yeah, and this isn't all of section 2. There's a second part to it that we're going to do next class. Okay, thanks for watching. Bye.